Somebody once said, we didn't move out of the Stone Age because we ran out of stones. You have to essentially develop new technologies that are better, not necessarily because you run out of something, but because there are other problems and better alternatives. In seeing the recent trends over the past 3-4 years, it's very clear to me that wind energy, in fact, is on a really steep growth path globally. So last year, in collaboration with a colleague and a postdoc, Raul Cal, we thought up a very nice research project to study the interactions between large amounts of wind turbines and turbulent wind that flows over the Earth's surface.
When you want to see what are the effects of these huge, massive structures on the atmosphere, you want to be able to quantify them. You want to recognize what is it that these structures do. What happens when you put these turbines too close or too far apart, not only horizontally but vertically, if you align them staggered or in parallel. So all of these are different effects that we want to be able to comprehend and quantify, rather than just going out there and building these massive structures, implementing them and not knowing what's really going to happen.
The modern wind turbine is in fact the largest rotating turbo machinery ever built. The way they work is the wind blows on them and they're essentially a inverted propeller. The kinetic energy in the wind generates a torque on the blade which makes it turn, and then that is connected to an electric generator. One of the convenient or wonderful things of fluid dynamics is something called similarity, which means you can, under some conditions, you can do tests at smaller scales compared to the real thing.
So what we try to do here in the wind tunnel is we scale everything down. Everything becomes very minute, very small. The models that we have here are 18 centimeters. In real life, they can go up to 100 meters, 150 meters high.
The experiment that we are about to conduct essentially generates a wind in the wind tunnel. Then we feed that airflow through an active grid.
An active grid, what that creates is higher levels of free stream turbulence. So this also helps us mimic what happens in real life.
Using something that is called particle image velocimetry, which is a relatively new measurement technique in fluid mechanics. We will take very detailed velocity measurements.
What we're trying to do is obtain the velocities and the flow field for that particular case in front and in the back of one wind turbine, after it has gone through 2 rows of turbines. And that is done to see the cumulative effect.
So the way this technique works is very simple, in fact. You seed the air with very tiny particles. They're so tiny that they're actually really following the airflow in great detail. Then you, with a laser, you generate a light sheet, which is very thin, and that light sheet is illuminated twice, so it's pulsed twice. And you take pictures of what you see. When we do the image analysis, we see that every dot is actually duplicated. There's 2 dots for every particle. And since we know the time difference between the 2 laser shots, we can find the velocity. And so we get a snapshot, an instantaneous snapshot of the air velocity at that particular point. Having these vectors, having these vector maps, allows us to actually calculate and evaluate how much flow of kinetic energy is going from one place to another place.
When you go out into the real life, into real flows, it's much more complex. So you cannot account for everything that is happening all at once. So here, at least, we start to understand control parameters that we can tweak.
As it is always with research, we don't quite know what exactly we will find. We don't know how exactly we will analyze the data after finding the preliminary things. That we tend to go fairly open-minded into subjects like this and let the phenomenon guide us and see what happens.